Hello. So in the today class I am going to explain what are the treatment of boundary conditions in FEM. Okay, so generally we have used one method, that is the elimination method, that is most popular elimination approach or method, you can say. So these methods are used to calculate the boundary conditions in the global equations. Okay, then second one, it is penalty approach. Okay, so these two are the different types of or different approaches that can be used for incorporating the boundary conditions in the global equations. Okay, so in many of our problems we have used elimination method to solve the problems. Okay, so like we have eliminated the global stiffness matrix and we have calculated the different unknown displacement or unknown deformations using this method. So sometimes in the examination they particularly ask you to use the penalty approach to calculate the unknown values. So in that case you should know the penalty approach method. Okay, how we can use the penalty approach? So there is a one simple concept, as the procedure it will be same till the global stiffness matrix. Okay, so in the global stiffness matrix where you have calculated as K U is equal to F. This is a finite element equation for a 1D bar element. Okay, now here there will be K value, like you will get in a two into two matrix, and also here you will get the displacement vector, and also there will be force vector. Okay, so if it is an 2 bar element you will get the global stiffness matrix or finite element equation in this form. Okay, so generally here there will be value like K11, K12, K21, K22, and the displacement commonly will take as U1, U2, and forces like F1, F2 it will be considered. Now in the penalty approach, for example, if there is one end and another end is free, and one end is fixed, another end is free. Okay, so two elements are there. It may be stepped bar, you can say, or anything you can take, uniform bar or stepped bar. To make more understanding, let us take this as stepped bar. One element, two element. Okay, so this is totally one element and this is the second element. Now in this equation let us find which is the maximum, okay, maximum stiffness value. For example, K11 or K12, K21 or K22, which will be the maximum value. So generally in this global stiffness matrix, generally whatever the diagonal values will be having maximum, any one of the diagonal values will be having maximum, any one. So that maximum value will be taken as C. C is equal to, it is a max K, K either I, J, okay, any one value, either K11 or K22 into 10 power of 4 to be taken, and unit should be Newton if all the values are meter, then Newton meter. If all the values are millimeter, then Newton per millimeter. That you have to take. Okay, that is the first steps. First you have to find the maximum stiffness in the matrix. Okay, now second one. So second one, it will be going to the element stiffness matrix. Okay, so in the element stiffness matrix, it should be modified. As you can see that in the figure, there one element, the node 1 is fixed, means the left hand is fixed. It means at this point, at k11, you should add the value of c. It means if it is modified, okay, so your k11 plus c you have to add, again k12, k21, k22, because here to make the equilibrium you have to add the value of maximum stiffness to that point, because where k11 node 1 is fixed, that's what we are adding with the c. If the both ends are fixed, then you have to add with k22 also. Okay, at node 2 also you have to add. So like that, this will be the modified element stiffness matrix. And also the load vector, okay, load vector f1 and f2 you have taken. Okay, so here it will be again modified as c into a1. Okay, because where f1 is again fixed and there will be no displacement, so again this will be 0. So a1 will be 0 because it is a fixed support. A is nothing but it is a displacement there. Okay, so using this method we can apply into our numerical, and we will calculate the different problems. Okay, so in the next video I am going to explain how we can apply the penalty approach method with any elements. Okay, and we will also calculate how the deflections we can calculate, and also we compare our values with the penalty approach with the elimination method. So both using the elimination method and also penalty method, both values should be same. Okay, both the values you will get same, and you can compare also, but a small difference can be acceptable because it's a numerical subject. Small tolerance can be acceptable. Okay, thank you.